Hi Algebra 2 students, this is going to be the video for our Monday class meeting. And in this video, we're going to go over more different kinds of linear systems that we can come across. And we're going to continue using our substitution and elimination processes. What we really want to focus on today is how we can take a look at application problems. So how are these types of linear systems used in the real world? What can they represent? What can they model? And then when we're approaching an application problem, how can we identify the different variables involved? So that way we can construct a system and then solve for the unknown variables or the unknown quantities involved. So you have a notes packet, and if you're in second hour or sixth hour, I'll pass out that notes packet for you. If you're in fourth hour, if you just want to check up at the front of the classroom, they'll be at one of those desks there. So that will just give you some space to work through the examples that we'll cover today. So on these slides, the first thing that I want to do is to get some more practice with elimination before we go about using elimination in our work with applications. So what we have here is an example that's similar to one of the problems that you saw in your homework. So in this example, our goal is still going to be to solve for x or y individually by eliminating the other variable. But if we come across a problem like this, our first equation is 2x plus 3y equals negative 6. Our second is 3x minus 4y equals 25. So in order to operate with elimination in an equation like this, we need to multiply both of our equations. We need to change at least one of the x's and the other x, or the other y and the other y. So we have to match up our variables. So if I take a look at these two quantities here, 2x and 3x, what I want to think about is the least common multiple, or LCM. And that's going to be the value that both of the numbers can be divided into. So if I think about 2 times 3, that's going to give me a least common multiple of 6. So 2 and 3 can both go into 6. So what that means is if I can make the x value 6, I would be able to cancel them both out. So let me grab a different color here. And I'm going to go ahead and take everything in my top equation and multiply it by 3. Because if I do that, that 2x is going to become a 6x. So let's see how that works out here. We'll have 6x plus 3 times 3y will give me 9y. And then 3 times negative 6 is negative 18. So remember, we can always multiply an algebraic equation by a number as long as we do it to every single term on both sides. Down here, instead of multiplying everything by 3, I'm going to multiply everything by 2, because then again, that 3x will become a 6x. So I will have 2 times 3x will give me 6x. 2 times minus 4y will give me minus 8y. And 2 times 25 is going to give me 50. Now, if I look at this setup, I'm going to have to subtract things to get them to cancel. So I want to subtract 6x minus 6x, that will all cancel out. Then I'll have 9y minus negative 8y. So remember, subtracting a negative is just adding. So here this is going to give me positive 17y. Then over on the right-hand side, I have negative 18 minus 50 more. So this will become negative 68. So then to solve for y, we're going to divide both sides by 17. And if we are dividing negative 68 by 17, we'll end up with a y value that's equal to negative 4. So that's perfect. We solved for our y term. And then we just want to go back and take that information to solve for x. So once you have your y value, you can either go back to one of your original equations, or you can use one of your modified equations. And it doesn't matter whether you use equation number 1 or equation number 2. Either way, you'll get the correct answer. So because equation number 1 just has smaller numbers, smaller coefficients, and a smaller constant, let's plug back in there. So here we'll have 2x plus, I'm going to replace the y with the negative 4, and that's equal to negative 6. So here this will become 2x minus 12 equals negative 6. I can add 12 to both sides. That will give me 2x is equal to, if I have negative 6 and I add 12, I'll get to positive 6. And then I can divide both sides by 2, and our x value is going to be equal to 3. So this is, again, just some practice with elimination and one of those newer kinds of examples where we have to change both equations, not just one, to be able to cancel things out. So our goal today is going to be to continue working with those strategies of elimination and of substitution to see what we can do to work with application problems. So let's check out this first one here. This one deals with Bella's pumpkin patch. So it's all about how much it's going to cost to do something at the pumpkin patch. Here it says, Bella's pumpkin patch sold tickets for a drawing to win a free set of pumpkins. Adults could purchase a ticket for $1.50 and children could purchase a ticket for $1. If 54 tickets were sold for a total of $70.50, how many of each type of ticket was sold? Now, when you take a look at these kinds of problems, what you really want to focus on is this last sentence here. How many of each type of ticket was sold? So we're always going to be solving for two different things in our linear systems. So in this case, X is going to be one of those things, and Y is going to be the other thing that we don't know. So we're trying to figure out how many adult tickets were sold and how many child tickets were sold. So it doesn't matter which one we call X and which one we call Y, as long as we know which one we're solving for. So let's call X number of children tickets, or child tickets for the drawing, and then Y is going to be the number of adult tickets. And the reason that we're trying to identify those variables is that it's asking us to figure out how many of each was sold for this drawing. So then we need to figure out, okay, what pieces of information do we have in order to set up a system of equations? So the first thing that we want to take a look at is where it says 54 tickets were sold. So my total number of tickets added together must be equal to 54. And that's where my first equation is going to come from. The number of my children tickets or child tickets, X, and the number of my adult tickets added together needs to be equal to 54 because that's how many I sold. So that's one of my equations. Then the other equation is going to come from the cost of the tickets. So it tells me adults can purchase a ticket for $1.50. Children can purchase a ticket for $1. So that's information I can put into an equation. I can say $1 times the amount of the child tickets plus $1.50 or 1.5 times the amount of adult tickets. That has to be equal to the total amount of money that we make here. So the total amount of money that we earned was $70.50. At this point, our goal is always then, once we have a system of equations, and in this case, we've got one that represents total number of tickets, and we've got one that represents total cost, then our next goal is to decide what's the best way to solve this equation. What's the best way to get X or Y by itself, get a value, plug back in and solve for the remaining variable. We could always go to graph things, but generally with application problems, that's going to be our least favorite technique to work with. So then we want to ask, should we use elimination or substitution? Oftentimes, substitution can be easier with application problems. The exceptions are going to be where it's very easy to cancel things out and to use elimination. So in this case, notice how I have an X here and there's really a 1 in front of it. Just like there's really a 1 in front of the Y, that's our coefficient. So if we want to solve for X and Y in this kind of scenario, it would be very easy to subtract because then my 1x minus my 1x means that those are going to go away. Then I just need to do subtraction. So here I have 1 minus 1.5y. That means I'm going to have negative 0.5y if I use the elimination. Then I have 54 minus 70/50. So that's the next subtraction step that we need to perform. So 54 minus 70/50 means that I'm going to have negative 1650 over on this side. So then to solve for y, I just need to divide by negative 0.5, divide by negative 0.5. And so we can plug this into our calculator, or we can remember that dividing by 0.5 is really the same thing as multiplying by 2. So when I multiply 1650 by 2, I'm going to get out that y is equal to 33 tickets. Then what I just need to do is to figure out how to solve for x. I just want to pick one of my equations to plug back into and then get out the x value. In this case, and most of the application problems that we'll see, the equation that does not have decimals will be easiest to plug back into. So what we want to do is to go back to our original equation, x plus y equals 54, but we're going to substitute in 33 for y. So then to get x by itself, we can just subtract 33 from both sides. And when we do that, x will be equal to 21 tickets. And that's our solution set. We're selling 21 child tickets, 33 adult tickets. That total gives us 54 tickets overall. And then if we plugged those also back into the second equation, we would find that 1 times 21 plus 1.5 times 33 would get us to 70/50. All right, up next we have another very similar problem. This one's about beverages. So let's work through this one and see whether or not we want to go with the elimination process or if we want to go with substitution. So this one asks us, you and your friend go to an inexpensive coffee shop to pick up beverages for your coworkers. You order 3 pumpkin spice lattes and 3 caramel apple ciders, and your bill totals $11.25. Your friend's bill is $10 for, this should say, for 4 pumpkin spice lattes and 2 caramel apple ciders. How much do pumpkin spice lattes cost? How about caramel apple ciders? So let's write out the system of equations and also define our variables. So we want to know how much one of the beverages costs and how much does the other beverage cost. So let's call X the cost of a pumpkin spice latte, or PSL, and then Y is going to be the cost of caramel apple ciders. So let's just say caramel apple ciders there. So we need 2 different equations. In this problem, you have an order and then your friend has an order. So it says that you're ordering 3 pumpkin spice lattes, 3 caramel apple ciders. So we can express that as 3x plus 3y, and then the total that you had to spend was $11.25. Then your friend has 4 pumpkin spice lattes and 2 caramel apple ciders. So we can say 4x plus 2y, and she's spending $10. So looking at this system of equations, notice that it's not going to be super easy to use substitution because we have different coefficients in front of every single variable. It's also going to be a little bit tricky to use elimination because we would have to multiply in order to get both equations to match up to a value. My recommendation when we go to analyze these for using substitution or elimination is to first look for the smallest coefficient. If it's a 1, you're good to go either with elimination or substitution. If it's something like a 2 here, check to see if every term in the equation is divisible by 2. If so, substitution is going to be pretty easy. So notice how the 4 here and the 10 here are divisible by 2. So if I want to get y by itself, I'll have 2y equals 10, I'm just going to simplify that without the decimal places, minus 4x.